Morning. So let's get started with today's discussion. Last time we were discussing the scheduling problem, task scheduling in distributed real-time systems, and we had said that these such systems, distributed systems, are becoming more and more important in real-time applications. So we'll see one of the major problems in these distributed real-time applications is clock synchronization. So let's look at how clocks can be synchronized in a distributed real-time system. So typically there is one clock at each node, and they are connected through a wide area network. So the transmission time here is quite significant, right, in compared to a multiprocessor system. But what are the uses of a clock in a distributed system? Can anybody answer this question? What do you think?
Time stamping the event.
Yes. So why do we need to timestamp? What sort of events? He said time stamping the events. What sort of events and why do we need to timestamp?
To know the sequence of messages, we need to have timestamp.
Okay. Yeah. Right. That is one thing. That message timestamping, to know what are the order of messages that have been sent from different nodes, or maybe even from the same node, right? So when the messages are sent from the same node, clock synchronization is not a problem, because it will timestamp on its own time and you can order it. But when messages are sent from different nodes, clock synchronization is important. So timestamping is one. Any other applications you can think of? Yes.
What is the latest information?
I mean, why do you need, what sort of latest information you are talking of?
How much the node load at a node? What is the latest information?
Okay. Yeah, so he gives another one, that finding the load position at an instant in different nodes. Yes. So let's see some of the applications and then we'll see how to synchronize. So we had seen that in the traditional use of a clock in a uniprocessor is to determine whether a task completes in time, right? We had said that there will be a timeout if it does not complete in time, and some exception situations need to be handled, that is, it misses its deadline. But in a uniprocessor, sorry, in a distributed system, we need to determine the message timeouts. You can't keep on waiting for messages and it will time out. And also timestamping, as you had said, and the timestamps give an idea about the age of the message, that also you had said, and you can order the messages. Now the clocks in a distributed system, they tend to diverge. It said that there are clocks across different nodes and they tend to diverge. Why do they diverge? Anybody has an idea?
Because of environmental conditions like temperature, pressure.
Sorry, error in the clock. I mean, what do you mean by error in the clock?
Drift from some standard value.
Okay, but why should it drift?
Because of that some environmental conditions.
Okay, so environmental conditions, why should that affect clocks? He says environmental conditions make clocks drift, but why should they make the clocks drift at all?
Power and so they are made of quartz crystals, so which are affected by this temperature.
Not clear. Can you please repeat?
Sir, the clocks are made of quartz crystals.
Quartz crystals. Okay.
So like they tend to be affected by the temperature, surrounding temperature and all.
Okay. Okay. Anybody has any other idea? He says that the clocks are crystal clocks, and the crystal frequency is affected by environmental conditions such as temperature. Anybody has any other idea?
Power failures for a fixed time.
Power failure? No, power does not fail. I mean, then the system will fail. See, after all, the clock is basically a small integrated circuit mounted on the board, the processor board, you will find a small IC is the clock. Okay, let us discuss this, maybe you will have a better idea. So, in a distributed system, it is very unrealistic to expect two clocks to run at the same speed, and this will call it as clock skew.
Sir, why don't they have same speed?
We will investigate. So, we will investigate that is precisely the question that I was asking, that why the clocks do not run at the same speed. We are going to investigate that. So, because they run at different speed, the skew increases with time, and once we are not sure of what is the skew. See, if the clocks have a constant skew, like one clock differs from another by 1 second, another by 5 seconds, etc., if these are constant, then it is not a problem. We can know the precise time of the different nodes, but these keep on increasing, and therefore, timeout and timestamp operations become meaningless. As some of you were mentioning, the clocks that are there in the computer are quartz clocks based on the principle of piezoelectricity, discovered in 1880, long back, by the brothers Pierre Curie and Jacques Curie. The main concept here is that when a voltage is applied to a quartz crystal, it distorts. So, this is a quartz crystal, if you apply a voltage, it will distort, and if you withdraw the voltage, the quartz would return to its previous shape, and in the process it will generate in turn a voltage, right. So, you had applied a voltage, it had distorted, and you remove the voltage, it comes back from its distortion to the original shape, and then it generates a voltage. So, this was the principle in 1880, but much later, about 50 years later, somewhere around 1925 or something, 23, this was applied to develop a clock. The idea is that a quartz crystal is like a RLC circuit, capacitance, inductance and resistance, and you know that every RLC circuit has a precise resonance frequency. So, just see here, this is the quartz crystal, and it acts like the equivalent circuit of this is this one, an RLC circuit.
Sir, what is C0?
These are some capacitance values, C0, C1 are capacitance, L1 is a inductance, R1 is a resistance.
Sir, this RLC is the bottom one.
No, this entire thing is a RLC circuit. Okay, this is the equivalent of this. It's a RLC circuit. It will have its own resonance frequency, right. So, how to model this as in this form, etc., let us not worry about it, but this is a model of this. Let us assume that there is a capacitance here across, and there is also capacitance, inductance, resistance involved here. Now, the first quartz clock was built in 1921 using this principle, and now you find it in the form of a IC mounted on your motherboard of a computer. But given this that these are quartz crystals, why should the frequency change, the clock frequency change across different nodes? Many reasons. One is that the angle at which the quartz is cut relative to the crystallographic axis, that determines the frequency, right. So, you can't guarantee that two quartz crystals are cut exactly on the same angle. The temperature and the size of the crystal. So, all these make the frequency vary widely, and even if you maintain the temperature and same different locations, right, you keep them in the same room, still the clocks will diverge. But just out of curiosity, nothing to do with this discussion, that why quartz? Why not? See, what is special about quartz? Why do you use this as the clock? Why not any other material?
Yes, some perfect crystal structure also.
Not really. Quartz is not the perfect crystal structure.
It exhibits piezoelectricity.
I am sorry?
It exhibits piezoelectricity.
No, but there are many other materials, they will behave similarly. It is not the only piezoelectric material. Okay, so the reason is that it has elastic property, right? It is one of the, and also it is not a good conductor of temperature. Otherwise, no, temperature will very largely affect its frequency. If it is steel or something, its frequency will largely be determined by temperature, even though steel is also elastic. So, quartz is an elastic material. Even if it gets disturbed, small amount, it will return to its original shape, and also it is not a good conductor of temperature. So, whatever you do, keep them in the same temperature, etc., the clocks will diverge. Given that fact, how do we make clocks agree on some time value, so that we can know the precise time in the different nodes? One node can know the time at which some event occurred. For example, he was saying one of the event might be what was the load at some instant. So, the agreed time that we will discuss can be different from the world time standard. The world time standard is called as UTC, Universal Coordinated Time, but this is not the full form, isn't it? UTC can't be, otherwise it should have been UCT. So, anybody knows why it is UTC is called as Universal Coordinated Time? Okay, if you look at it, it is very funny actually. The French for the Universal Coordinated Time is CUT. I mean that is a French word actually, and because there was a controversy that it should be named as Universal Time, Coordinated Universal Time, or Time Coordinated Universal or something, right. So, they took a middle path and they just made it UTC, which neither is a full form in French nor in English. Anyway, so it is Universal Coordinated Time based on the International Atomic Time, same here, TAI. It is maintained at Paris by averaging a number of atomic clocks from laboratories around the world, and UTC signals can be obtained through GPS receivers, and also these are transmitted by some special radio stations. So, one thing is that the clocks can be made conformant to the UTC, but that would be much more expensive than making them agree on some standard time value, right. So, UTC is not used in most of these distributed systems. They determine a time based on their own times.
How can that be made to agree on it?
That is what we are going to discuss, how the clocks will agree on a standard time. We are just going to discuss that. So, those are the clock synchronization mechanisms. Roughly there are two main mechanisms. Now, one is called as the internal clock synchronization, the other is called as the external clock synchronization. As the name says, internal clock synchronization will be basically the time value will be determined based on some internal clock internal to the system. Maybe one clock, maybe many clocks, but all the clocks are internal. Whereas in external clock synchronization, we will use an external clock like the UTC. Okay, so in internal clock synchronization, all clocks are synchronized with respect to a clock internal to the system, whereas in the external clock synchronization, the clocks of the system are synchronized with respect to some clock which may be external to the system. For example, UTC, but it can be any other clock. In an external clock synchronization, we will have a master clock which can be UTC or any other clock which transmits time to all these clocks frequently, and they keep on setting their time according to the master clock. The implementation of this is simple, but unfortunately it is not used. As we were saying, let us see the advantages and disadvantages of the external clock synchronization. It is easy to implement, just keep on setting that time, sensing the time and setting it. Zero communication overhead on the internal network, because these are broadcast to these nodes. But the disadvantage is that it is expensive to have a GPS receiver at each node, and possibly that is the reason why external clock synchronization is not used in distributed real time systems. And also, depending on the location where it is deployed, the availability of the signal may be weak, it may fade and so on. So, the one that is actually used is internal clock synchronization, and if we look at internal clock synchronization mechanisms, there are two types. One is the centralized synchronization and the other is distributed synchronization. In a centralized synchronization, as the name says, we have one master clock. One of the clock of the system will be the central clock or the master clock, and the signals, the clock values from that will be used to synchronize all other clocks. Whereas in a distributed synchronization, the clock values across many clocks will be used to synchronize the different clocks. So, here one of the clock, the node will broadcast its time, the node of the clock will broadcast its time, and other clocks, different nodes will set their time according to this. Whereas in a distributed clock, no clock is taken as the master clock or the reference clock, and the clock values, the average of all clock values, not all clock values, as you will see, many of the clock values are used to set the time which is agreed by all clocks. Now, first let us look at the centralized clock synchronization, because we will see that this is also not very popular. It is not that it is not used, but not very popular because it has some problems. So, here one of the clock is designated as the master clock, also called as the timekeeper or time server, and the other clocks are slave clocks, and they keep in sync with the master. So, this is the master clock, and all other clocks, this keeps on transmitting, broadcasting the time values, and the slave clocks keep on setting their time according to the master clock. Simple mechanism. Okay. In the system, it just keeps on broadcasting the time and they keep on setting. The server broadcasts its time every delta t time interval. Now, let us see slightly more detail of this. So, periodically broadcasts and the cycle is delta t. But one of the main problem here, not problem, one of the issues that we need to address if we are going to use a centralized clock synchronization is to fix the value of delta t, how frequently it should transmit, because if there is transmits too frequently, it is a problem. And what is the problem? It transmits, communication overhead, simple thing. The clocks will be in synchrony, but there will be large communication overhead, and if it transmits less frequently, then the clocks will go out of sync. So, if delta t is too small, there are frequent broadcasts from the time server and result in high communication overhead, but there will be good synchronization among the slaves. On the other hand, if delta t is too large, then the clocks will not be synchronized towards the end of this delta t time interval, right. They will get synchronized, and as the time progresses, they will become unsynchronized, they lose synchrony, and again after delta t they will get synchronized, right. So, during this interval delta t, the clocks might drift too much, which will be unacceptable. Now, let us assume that the maximum drift between clocks that is permissible by our application is some rho. See, we had earlier discussed about scheduling issues and so on, and there we had assumed, I think, some communication time we had assumed, right, in distributed systems. But this is another thing that we need to assume, that what is the maximum drift between clocks, and that we need to bound. Let us say, compared to our task completion times, which is of some milliseconds, several milliseconds, we need to have a rho small enough so that it will not really affect the schedulability of the tasks, right. So, you need to fix it to some value, should not exceed rho. Now, what the clock manufacturers actually give for these clocks is actually the rate of drift. It is not the maximum drift, but the rate of drift. The rate of drift is how much drift between the clocks will occur per unit time, and that is rho. I am sorry, I think I told you that this is the maximum drift. No, this is the rate of drift, maximum rate of drift. So, this is what the manufacturers will tell you, that see, we have manufactured these clocks and the coarge is caught precisely and all those, and but we can guarantee you a maximum rate of drift, that is drift per unit time, is rho. It can be less than rho. Now, suppose the clocks are resynchronized after delta t interval, then the maximum drift of a one clock, that is one slave, from the master will be rho delta t. Do you agree with this? Because the rate of drift is rho, and they synchronize, set their time with the master, and let us say the communication time is known to be constant, because if the communication time is, we can't fix a bound on that, then again this will not work. Now, the maximum drift between any two clocks is 2 rho delta t. So, why is this 2 rho delta t? Yeah. So, one may drift, become a slow clock, and another is a fast clock. So, one has become slower by rho delta t from the master, and another has become faster by rho delta t. So, between these two slaves it will be 2 rho delta t. Now, let us see what are its advantages and disadvantages. The advantages is that not really very difficult to implement. Just designate one clock, good clock, as the master, which transmits the time frequently. Need to calculate the time frequency at which it will transmit. The communication overhead is moderate, because it is after all one clock, one node just keeps on broadcasting every few seconds. But one major problem of the centralized clock synchronization is single point failure. What if the master clock fails? So, if your application is actually safety critical, failure cannot be tolerated, then this centralized clock synchronization is not a good solution. The clocks will fail if the master clock fails. Now, let us just work out an example using this simple thing that we discussed. Suppose we have 6 clocks in a distributed system and we want to use the centralized synchronization scheme, and we can assume that the rate of drift between the master and another clock or between any 2 clocks is 5 into 10 to the power minus 5. Do not have a unit here because it is rate of the drift, this much time per unit time. Now, let us say we want to maintain the maximum drift between any 2 clocks to be restricted to 1 millisecond. So, what is the frequency with which the master needs to broadcast, and also need to calculate how many messages need to be transmitted per hour. Can you do it, or should we look at the answer? 2 rho delta t is equal to 1, yes, okay, not very difficult. So, he already has said that 2 rho delta t is equal to epsilon, which is equal to 1 millisecond, or in other words delta t is equal to 10 to the power minus 3, that is 1 millisecond, right, divided by 5 into 10 to the power minus 5, which is equal to 20 second. So, every 20 second it needs to transmit the clock value. But what about the message overhead? The master needs to transmit n minus 1 messages per resynchronization interval. So, was the calculation all right in the previous slide? Some of you were mentioning something. Was the calculation all right? Yes? 10 to the power minus 3 by 5 into 10 to the power minus 5. So, 100 by 5.
Divided by 2.
Okay, 2 is there. Okay, yeah, right. Is that 5 in 10 to the power minus 5? Yes. Okay, I think that is a mistake I have done here. Forgotten 2 here when I have taken this side. So, 2 into 5 into 10 to the power minus 5, right. So, this will become 10 second, right. Okay. So, that is a mistake I have done here while calculating this anyway. So, that should be 10 second. Transmission broadcast time is 10 second. Now, how many messages need to be transmitted? The master transmits 5 messages for each resynchronization interval. So, that is 60 into 60 divided by 10 it should be, right. So, which will be 360, and then the number of messages transmitted per hours will be 360 into 5, right, 1800, simple thing. Now, let us see the distributed clock synchronization. So, here as we were saying there is no master clock. And here all the clocks, they exchange their time values, and each clock computes the average of the time values and then sets its clock accordingly. This is the simplest scheme that can happen. So, there are many clocks here in the distributed system, they just keep on broadcasting their own time frequently, periodically and frequently, and then after a clock receives all the time values, it computes the average,
time of
all the clock values that are received.
from
All other nodes have sent values, isn't it, including its own clock. So, it just finds out the average of all clock values in the system. See, everybody computes the average of all clocks, right, C1, C2, C3, C4, this averages, this also averages C1, C2, C3, C4. So, if all are averaging all the clocks, then they will agree, isn't it? Then the clock, they will agree on the time, because after all they are averaging the same set of clocks. But what if some clocks are bad? A bad clock may not send time, or it may send erroneous time, right. Instead of sending 5 hour and 40, it will send some 6 hour 50.
still they will be same, right? The average will be still same.
No, but the bad clock might not always send 6 hour 40, right? It might send 7 hour sometime. It may not send anytime, and sometime it will fail, right? It was sending and then the bad clock failed. So, then everybody will have to reset their time back, isn't it? So, once a clock becomes bad, the time value will jump, isn't it? Either plus or minus. So, the clock was already differing and then suddenly it has stopped calculating, stopped sending the time. That will be a problem. It is not that all clocks can still agree and that is not a problem. Okay. So, the solution he says there that see it is not very difficult to handle, that even if after some time some clocks can become bad, but the thing is that the bad clocks can be identified by large drifts. So, if it is 5 hour 40 and it has sent a time 6 hour 50, can immediately each node will know this is a bad node, bad clock, and they can eliminate it from computation. So, if a clock drifts larger than the manufactured specified tolerance, then the time values can be ignored and the bad clocks may even stop keeping the time altogether, they might not transmit the time, does not matter. So, handling bad clocks is easy, they can be easily identified because they differ by large values and the time values can be removed easily. But a more serious problem is the Byzantine clocks. Bad clocks are not a big problem, can be easily handled. The problem is the Byzantine clocks. A Byzantine clock is a two-phased clock. Actually, it's based on some story of Byzantine generals. I think some Rome or somewhere near Rome actually. There was a kingdom, Byzantine, and there the generals go to different places, they are positioned in different places and they coordinate their attack. So, the problem is that what if some of the generals try to confuse the other generals and trick them at attacking the wrong time. So, they tell one general one thing or they confuse them. A Byzantine general will confuse the other general, he will tell one general that see it is not the time to attack and will tell another general that see we should attack now, right. So, that they will lose it. So, a Byzantine clock transmits different values to different clocks at the same time. See here C1 is a Byzantine clock and it is transmitting some t plus e to C5 and t minus e to C2. See if E was large enough, let us say t is the time at C5, if E was large then C5 would have eliminated that, but it is acceptable time value within the bound. But here also it is within bound, but it is showing two different values. Now, if they compute the average, there will be a difference in time, but how much difference in time? If there is a Byzantine clock and we know that the maximum drift between clocks is let us say rho into delta t. So, what will be the effect of a Byzantine clock on the clock synchronization? Okay, we will just discuss about that. But the first question is it possible to have good clocks synchronized in the presence of Byzantine clocks? Answer is yes, we can synchronize them if no more than 1/3 of the clocks are bad or Byzantine. So, out of 10, if you have 3 clocks bad, then we can synchronize them. But if out of 10, 4 are bad, then whatever we do, we can't keep them synchronized. Or let us say we have 9 clocks, if 3 are Byzantine, then we can't synchronize them. It should be less than 1/3. Now, let us show how to do this. Why 1/3 of the clocks? If they are bad, we can synchronize, and no more than 1/3. Assume that there are n clocks in the system, and the clocks are to be synchronized within some epsilon time units of each other. Now, when a clock receives a time broadcast, it checks against its own time. If it differs by epsilon time units, then the received time values are ignored because it has drifted more than epsilon, right? The drift is to be restricted to epsilon, isn't it? So, if it has drifted more than epsilon, the clock is bad, time value is ignored. But this does not eliminate the Byzantine clocks, right? It is only eliminated the bad clocks, and each clock averages the time values, good times, and uses this as the time value. So, this is the pseudocode for that simple thing here. See, the good clocks to start with is n, right, a global variable set to n. Now, it computes, this is one interval for synchronization. So, what it does is, if the clock drift is more than epsilon, it is a bad clock, it just reduces the number of good clocks, and if it is a good clock, if it is within this bound, it just computes the total, and then it just computes the average. So, that will be total time divided by good clock, right. Ci is its own time, and j is the time received from all other clocks, n minus 1 other clocks. So, it will average out the time values of n minus 1 clocks, and then add its own time, and then average it out, right.
So, in this previous
Yes.
that Ci minus Cj
Yes.
should be greater than epsilon.
Oh, what did we have? Let us see.
Ci minus Cj, if it is greater than epsilon, then
Yes.
we call it a bad clock.
Yes.
Suppose Ci has drifted by epsilon, Cj has drifted by 2 epsilon.
No. See, every clock, see, our goal is to keep 2 clocks synchronized within epsilon.
Yes, sir.
We do not bother about which is drifted. So, if the time difference between the clock that has received it and another clock is more than epsilon, then the other clock will be assumed to be bad.
Okay.
Is that okay?
Suppose one has drifted by epsilon, other by
Don't matter. I mean, it does not matter whether the clock has drifted or not. Our goal is to keep them synchronized within epsilon, that is given. So, within delta t, if they have drifted more than epsilon, know that the other clock is bad. This clock assumes, the local clock assumes that the other clock is bad, it has drifted too much, more than the permissible amount. Is that okay? Okay. Okay. So, now let us look at a result. The result is the effect of a single Byzantine clock. So, this will state in the form of a theorem that a single Byzantine clock can make any 2 arbitrary clocks to differ by 3 epsilon by n second, where epsilon is the maximum permissible drift between 2 clocks, that is C minus epsilon mod, sorry, Ci minus Cj mod is greater than epsilon. So, that same thing. So, epsilon is given to be the maximum permissible drift between 2 clocks, and n is the number of clocks in the system. And what this theorem claims is that the effect of a single Byzantine clock would be to make two arbitrary clocks at most differ by 3 epsilon by n. I think this was the question that I was asking you, that if we have one Byzantine clock, what will be its effect on other clocks, because it will confuse the other clocks, is not it? Send a high value to something and a low value to something, but and since the bad values, it cannot send really bad values, it will be sending within the epsilon limit. So, one it will be sending plus epsilon and another minus epsilon, right, and the effect of that is to make two clocks differ by 3 epsilon by n. Let us see how we get that, not very hard. See here, we have a bad clock here C1, let us assume 3 clocks. So, this is the sketch of the proof, we will consider for 3, you can generalize to n very easily. So, the sketch of the proof is like this, we assume that 1 is bad. Of course, in this situation, no, 1 is bad out of 3, we can't even make them synchronized within any given bound, not only epsilon. So, just for our own understanding, let us assume that C1 is a bad, it is not a bad, it is a Byzantine clock, C1 is a Byzantine clock. Send C3 minus epsilon to this and sends C2 plus epsilon to this one, right, and C2 and C3 also can differ by epsilon, see there. So, C2, C3 are the good clocks, C1 is the Byzantine clock, and C1 transmits C2 plus epsilon to C2 and C3 minus epsilon to C3. Now, due to Byzantine clock, C2 and C3 differ by 3 epsilon. Do you agree with this? Because they themselves differ by epsilon at the most. If you can assume some time t here and t plus epsilon here, or you can assume t here, that may be easier, it does not matter. So, t here, t plus epsilon here. So, this becomes the time value computed here will be t plus epsilon, 2t plus epsilon, is not it? So, we will just see the calculation in more detail. So, it is not hard to see that they differ, the two clocks will differ by when they compute the total time, right. This clocks computes the total time from all clocks from C2 and C3, and this clock computes the total from C2 and C1, then the total will be differing by 3 epsilon, and then after averaging that will differ by 3 epsilon by n. That is the sketch of the proof. So, let us see the calculations here. So, see here, C1 is the Byzantine clock. Okay, I should have used a different color here, that would have been easier. Anyway, so this transmits C2 minus epsilon to C2 and C5 plus epsilon to C5. And this will compute the total, let us say due to all other clocks C3, C4 etc. This is M, okay, some part has got missed here. So, this will be 3 C2, so this is C2 and this is, they in turn differ by epsilon. Okay, let us see this one, this is part is cut here. So, let us see the value that is computed by here. Let us assume M is the time value received from all other clocks, sum of the time values from all other clocks. Now, let us see the impact of these 3 clocks that we have shown here. So, the value computed by C5 will be 3 C2 plus 3 epsilon by n, and this will be 3 C2 plus m by n. Let us assume that this is C2 and this will be at most C2 plus epsilon, isn't it? And this is and this is C1 and this is C2. So, this has got C2 minus epsilon. So, it will become 3 C2 plus m by n, and this will become 3 C2 plus epsilon plus m by n. Is that okay? Because it has got the time value transmitted from here is C2. And this has got time value transmitted from C5, which is C2 minus epsilon. Okay, so this will become. So, should we calculate out the details of the how the clocks send their time and they are averaged? Okay. So, let me just calculate here. See, there are many clocks here. So, let us assume that these are the 3 clocks we are worried about, and we can extend that that argument to any other clocks, any other 3 clocks. So, this is the one which is Byzantine, and let us assume this is C1 and this is C2, and C1 and C2 differ from each other by epsilon. So, the Byzantine clock B will transmit C1 minus epsilon to C1, let us assume, and it transmits C2 plus epsilon to C2, let us assume, the worst case. So, the sum calculated by this one, this clock C2 will be C2 plus epsilon minus plus C1, let us say plus epsilon, it sends a plus epsilon here, they differ by plus epsilon. Okay. So, no, this is okay, no, this has transmitted its own time. So, that is okay, okay, C2 plus epsilon, right. So, this will be 3 C2 plus 2 epsilon, right, in this situation. Now, what about this one? This will be its own time is C1 plus it has got C1 minus epsilon here, C1 minus epsilon, and whatever the time it has received from here, and of course, this will get m from all others, let us say it gets m, the same m is got from all others, that we can ignore. But what about this one here?
Actually, that sum is wrong.
Sorry,
That sum is
this is wrong, is it?
Yes.
Why?
actually
C2 is obtained here, C2 plus epsilon. So, C2
C2 plus the second one is C2 plus epsilon.
and this has got C2 plus epsilon, that is all right. So, 3 C2 plus 2 epsilon.
Actually, what we have to add is C2 plus C1 plus C2 plus epsilon. We have taken C2 2 times.
No, 3 clocks, there are C2, 3 C2 plus 2 epsilon. Now, let us see here. So, this one we have C1 is its own time and it has got C1 minus epsilon here and it has got C1 minus epsilon here, right. So, this is 3 C1 minus 2 epsilon, but we know that C1 is C2 minus epsilon, is not it. So, this becomes 3 C2 minus epsilon okay, C1 is C2 plus epsilon, right, minus 2 epsilon, C1 is C2 plus epsilon. So, this becomes 3 C2 plus epsilon plus m of course, and this becomes 3 C2 plus 2 epsilon plus m. So, they differ by 3 epsilon, just do the calculation.
Only 1 epsilon. We are getting only 1.
But now we are getting only one.
1 epsilon,
Actually, the
okay,
mistake
okay,
is
okay.
that in the first calculation is C1 plus C2 plus that given by Byzantine, sir.
Okay, let us see. C1 is C2 plus epsilon,
No, sir.
and
What we assume in the beginning
yes,
is that
yes,
C1, we are taking C1 as reference.
yes.
C2 is equal to C1 plus epsilon. We assume like that in the beginning. C2 is
No, see, the Byzantine clock is sending here C1 minus epsilon. If it is any less than that, this will reject it, right. This will send C2 plus epsilon. If it is any more than that, it will reject it, right.
and actually C2 is ahead of C1.
C2 is ahead of C1, yes.
So C2 is equal to C1 plus epsilon.
Yes, C2 is C1 plus epsilon, yes.
So
Okay, this should be minus, right.
no, sir. Here we will get again the difference. Only in that calculation we
I'm
can
sorry?
directly get 3 epsilon.
Instead of replacing the C2, C1's, the C2 in place of C1,
Yes.
why don't we just keep it as it is and then
Okay, use just one clock value, is it?
yes,
Okay, let's do that. I think it's become unnecessarily complicated. So let's assume one is the Byzantine clock, and we have one clock C1 and another clock C2, and this sends C2, will use it as C1 plus epsilon. C1, that will simplify as he says. So we will use this clock's value as C1 plus epsilon, and the Byzantine clock will send here C1 minus epsilon, and to this it will send C1 plus epsilon, sorry, C1 plus 2 epsilon,
Yes.
C1 plus 2 epsilon. So the time value that this gets, this clock, is C1 plus C1 minus epsilon plus C1 plus epsilon. So this becomes 3 C1, and we have other clocks of course, which have a constant time value that is transmitted plus m, and this one gets C1 from here plus C1 plus epsilon its own time plus C1 plus 2 epsilon. So this is 3 C1 plus 3 epsilon plus m. Okay, so that simplifies, just considering one clock rather than using 2 C1 and 2 values C1 C2. So that was leading to unnecessarily complications. So easy to see here that the effect of the Byzantine clock is to make two clocks, even when we have n clocks in the system, to differ by 3 epsilon, and the average of that after it is computed, it will become 3 epsilon by n. So we will just stop here, and we will continue with discussing about how to compute the frequency with which you need to transmit clock values, so that even in the presence of Byzantine clocks, when 1/3 of the clocks, less than 1/3 are Byzantine, we can still keep the clocks synchronized within a given bound on the drift. So what do you think? Will the bound of the drift, let us say we want to keep them within epsilon, so should they transmit more frequently, or should they transmit less frequently in the presence of Byzantine clock? Let us assume that there are two situations. One is there are no Byzantine clock, another is there are Byzantine clocks. So should they transmit more frequently or less frequently? More frequently, because no, we want to, let us say, keep them synchronized within 1 millisecond. Let us say the effect of 1/3 Byzantine clock is to make them drift by 0.5 millisecond. So by the time the drift becomes 0.5, we need to have a broadcast. So we will stop here, and we will continue our discussion the next hour. Okay, thank you.